then it's decision tree. What is decision tree? I have a data set. This time we're going to test the whether this person has a heart disease or not, based on whether they have chest pain, whether they have a blood circulation, and whether they have blocked arteries. A decision tree is like a tree. It has roots, it has leaves, and also it has these branches, which we call yes and no. So it looks like a leaf, looks like a tree. So what are they? Let's say we have a chest pain. I say my roots to start from chest pain. So if this person has chest pain, then it will have this person will have a heart disease. Is that a yes? Okay, 2 votes for the yes and 1 vote for the no. And if this person doesn't have a chest pain, the chance of heart disease is like, in this data set, there is 0 yes and 1 no. So in this case, like, you keep continuing to have a different type of like condition. In my case, the first one is root, because this is the starting point and there is only 1 root. But you can have as many leaves as you want. And what is in the between is a node. We call it root, node, and leaf. So in this case, you have this tree, these tree branches, like a lot of branches, like going to as many possibility as possible, going as many root as possible. And you choose, okay, yes and no, and yes and no. And at the end, in the leaf, you choose, okay, the heart disease is like 2 in this data set. The number of no heart disease is 1 in the leaf. That is a decision tree. So you can choose any condition like you want. So the root can go to 1 node, say block arteries, and this chance of getting heart disease. And if it's a good blood circulation, it's yes, like no. You get that. So what is gradient boosting algorithm? It is based on the decision tree. So basically, what we're getting is a probability of whether it gets heart disease or not. And so in each iteration, it actually updates probability to give it a kind of, I'll say the gradients improvements. You keep adding these like little trees up. Oh, I think I missed it. You keep adding these improvements of new probability. Eventually, you will have the result of probability. So in this case, you keep improving it and to get your final result. And we also talked about principal component analysis. What are they? We have a bunch of dots and we want to do dimension reduction because, okay, in my case, I only have 2 dimensions because I only have an x-axis and y-axis. That's 2 dimensions. But I think 2 dimensions is too big, still too large for me. What I would do is I will change that, turn that into 1 dimension. What do I do? In principal component analysis, it finds the direction where it has maximum variance. Where is my maximum variance? It's this direction on the red line. So on this direction, my data set is the most dispersed, like just stretched, expands to the maximum and minimum. And then I'll just project this data set into this 1 dimension. Now I have a 1 dimension data, which is my red dot. My new axis is my red line, and my data set is my red dot. It becomes a 1 dimension data. So that's principal component analysis. And then neural networks. We have neural network. Oh, so it will take a little bit longer to recap. If you want to know more, go to either the session 1 recording or the session 2 recording. There is a more comprehensive description about the neural networks. So basically what neural networks is, we can look at the right side, basically. Forget about the max pool layer, convolutional layer. Just look at the right side. Each dot is a node in the neural network. We call it a node. So I have a data set. If you can think about, just think about the red, yellow, and green dots in a 2D space. That is my feature. My feature is my x-axis and my y-axis. That's 2 numbers to build up a dot in a 2D space. And then I'm going to expand this feature into so many nodes, which is I chose a very interesting color, the pink, I'll say the pink dot in the flattened layer. And then I calculate it. And to get some yellow dots, like yellow nodes, yellow nodes on the right side, which is called dense layer. And then I keep calculating to the blue dot, which comes to a result of whatever I want. So neural network is just these layers after layers of nodes to like a way to calculate things. So that's a recap of session 2. Now we can finally talk about Naïve Bayes. The reason we didn't talk about Naïve Bayes last time is because it is a very, I would say, very big topic. I was thinking the way to explain it in a simple way, in image, and I couldn't think about one. Like, it has to have some equation involved, and you will hate it if I try to explain everything, dump everything into 5 minutes or 10 minutes to talk about Naïve Bayes. So that's why we open up a 3rd session talking about it. So in this case, in this session, we're going to learn the concept of Naïve Bayes. You will understand what it is. We're not going to work on setting up a machine learning model because I think that will get too complicated. So today, you're just listening. If you have any questions, feel free to ask me. So, Bayesian classification. What does it do? Bayesian, Bayes rule, Bayesian theorem, Bayes theorem. They are all similar things. It talks about probability. What does it do? It can detect spam classification, which means I have an email. In this email, I have a bunch of features. Each feature is my word. Like, dear friends, I'm writing this email to. So each word, dear friends, I am writing. Each word is a feature. And I gave the model all these features, and it needs to come out a result, say whether it is a spam or not. The same thing goes to medical diagnosis. It's like the example we made earlier, which is okay, so this person has a chest pain. My feature would be yes or no chest pain, yes or no, I don't know, back pain. And the result is yes or no, this person has heart disease. Or something like weather forecast. My input X feature, like the feature we call them X, is what's the temperature? What is the, I don't know, is it sunny? Oh, well, sunny is the weather. So what's the temperature of this area? What is moisture level of this area? Maybe what's the pollution level of this area? based on those information, we get output says, okay, it's going to run or not. And also we have a digital, it can be used in digital recognition, which is like, I have a picture of number 1, 2, 3, 4, 5. So which it is. Like, what is the problem? In all these applications, you can hear me say, we have a lot of features, My feature is called X. Let's say in one case, I say, I have the temperature, one feature. I have the moisture level, one feature. And I have the pollution level, which is another feature. In this case, I have 3 features. I give it a number D, like dimension. Each feature is a dimension. That's once you put the dimension word in, it sounds so much cooler. So yes, we have D features, which is D dimension. And based on that, I want to predict my label, which is, okay, it's going to run or not. Then we come to the equation part. What is it? The Bayes classifier is actually calculating the probability of whether it's going to run or not on the condition of my D features. Here, the P in the middle is called the probability. Y is my label. The straight line basically says it is on the condition of x1 to xd. So based on this probability, it's normally a curve or a distribution. Then what I need to do is I need to find the maximum probability. Otherwise, if I say, okay, the probability of run when the temperature is like, I don't know, 20 or 40 is 0, then why do I care? Like, I want to see where is the maximum. So what happened is, like, in front of it, there is a max. That's the maximum. Based on y. Y is the argument, that's why the function looks like that. So I know it might get a little bit too complicated, but please feel free to interrupt me if you have any questions. So for example, I have picture. It's a digital picture of binary data. In this case, let's say it's 28 by 28 pixels. I have 28 pixels on horizontally, and I have 28 pixels vertically. And the blue is represented by 0, and the red is represented by 1. I want to feed it to a classifier, which is also called a model. And then I want the output to be 5. That's what I want, because when I look at this picture, I know it's 5. So what is my feature? In this figure, my feature is the number of each pixel. So what is D then? How many features do I have? The number of my feature is 28 by 28. That is a lot. And then because each X is a pixel, and these numbers belongs to 0 or 1, which means there's only 2 chances, like 2 possibilities, 0 or 1. And then what is my Y? My Y is my result, my label. I'm giving it, okay, so my label can only be 5 or 6. You need to choose one from it. We need to predict whether it is 5 or 6. And we're going to use the function we just mentioned. First of all, let's clarify some nouns we're using. So we have the probability of y, the label, on the condition of showing up all these x, all these pixels. And this is a posterior. And then what this posterior equals to, because it is really hard to calculate the left side, to make the calculation simpler, to make it so much better for us to actually do it, we're going to transform this function into something else, which is easier for us. That's why we have Bayes rule, which is this equation. What it does is I hope that didn't scare you with the leak of the complicated equation. So what it does is that it transfers the equation from the left side to a different equation, which is likelihood multiplied prior divided by evidence. So what is likelihood? The likelihood is, okay, I'm saying on the condition of label y, on the condition that the picture is 5, the likelihood or the probability of each pixel, and then multiply the probability of y equals to 5, the chance of this picture being 5, divided by the evidence. What is the evidence? It's your observed result. So this is Bayes rule. It's basically kind of equation transferred, like they are equal to each other. So I'm trying to change it into an easier way to calculate. So what does that make the figure, like calculating, predict whether the figure is 5 or 6, look like? I'm expanding it. What am I expanding it to? Remember, we are testing whether the label is 5 or 6. So on the condition of all my pixels, the possibility of y, the result being 5, is equal to the first two lines, they might slightly squish together, but the first two lines, because the equation is too long, it is the same as this one. They are the same equation. It's just y equals to 5 now. So the possibility of this picture is 5 on the condition of these pixels is calculated by these pixels on the condition of this label being 5, multiply the possibility of this picture is 5. And what I'm going to add here on the bottom is how it transfer like that. In this case, I have a whiteboard I can show you guys. You cannot open it up. Very helpful. Let me stop sharing. Sorry, give me a second. Okay, feel free to add anything. So I hope everyone can see this. We have, yes, we have probability of x1, x2, all these pixels, xd. So what it does is that the possibility of these pixels showing up, regardless of it's being distinguished 5 or 6, is probability of x1 to xd on the condition of y equals to 5, multiply the condition, multiply the possibility of y equals to 5 plus xd on the condition that y equals to 6. We know that there are only two possibilities, two chances of this figure being 5 or 6. So it can only be 5 or can only be 6. I think what would be useful is to have this. There are two functions might be helpful. Is like, what is this condition of let's say A, probability of A happening on the condition of probability B, is that the chance of A and B happens together divided by the chance of B happening. What is the chance of A and B happening together? Is the combination of A and B. So that is the expansion of this. In this case, we can transfer this x1 multiplied to xd to this equation. Then let me open up okay, I hope this long equation didn't scare you away. Now we know it. Okay, these are the expansion. Then what happened is that, okay, I'm going to make assumption. It still looks too complicated. How can I know the possibility of all these pixels happening on the condition of this image is 5, like to be this? There is another equation. There is an assumption, which is a simplified way. So this door shape symbol is a multiply symbol. It says, okay, my function can be assumed to be all these pixels are independent. The pixel on my left can be 0 or 1. I don't care about it. I am making my own decision to be 0 or 1. So in this case, we can simplify this function into, okay, my possibility of this pixel, this specific pixel 1, on the condition of the image being 5, multiply the possibility of my second pixel being 1, on the condition of the picture is 5. Then our super complicated function still becomes a super complicated function, which looks very long. Then we can reduce this to another way, like say, okay, this is a function we're going to use to calculate whether this image is 5 or 6. So we have a bunch of training data sets. In this case, I have 7 by 8, which is 56, 5, and 56, 6 images. In total, I have 112 images to train my model. What do? I need to calculate this equation. But what are they? What is the probability of this image being 5? What is the probability of x1 being like the first pixel being 1? Or what's the probability of the first pixel being 0? What is it? So they are all based on, think about it, they are all based on our training data set, which are these images, 112 images. All this probability are calculated based on that. Otherwise, I don't know what's the probability. I can only work with the data set I have. So what is the probability of an image being 5 based on my training data set? So I have this whole 112 training data set. Now I'm throwing at you an image. Without even looking at it, can you tell me what is the possibility of this image being 5? Anyone want to answer it in the chat? Let's make it interactive. Okay. Well. Okay. I can answer it. So I have a bunch of image of 5 and 6. And I have 56, 5 and 56, 6. Oh, that's an interesting number, 56, 5 and 56, 6. Ooh. Let's see a chat. The first, yes, the first 5 looks like a 6. I know that's the difficulty of it. They make it so similar, but the one who wrote it says it's 5, so it has to be 5. So yeah, like the chance of I throw you an image based on these data sets, then I say, okay, there are 50% of the chance an image is 5, because from what I learned out of these 112 data sets, 112 images, there's only 2 chance, like there's 2 possibilities, like 5 or 6. Then 50% of the chance it will be 5. So we have that directly. All we need to calculate is the number of image being 5, which is 56, divided by the total number of image, which is 112. That's 50%. Yes. Then my next question is, what's the chance of the first pixel being 1? Let's say the first pixel being 1 is 1 is white and 0 is black. So the chance of the first pixel being 1 on the condition of the picture is 5. So what does it calculate? Is actually of all these pictures where the image actually says 5, out of all these numbers. Let's see if we need so out of all these images, my probability of my first pixel, oh, that's 1, being 1 on the condition that my image is 5 is that I'm going to calculate the number among all these number of image, the number of image 5. So what is on top on the numerator is that in these images, in this image 5, how many image have the first pixel as 1. So in this case, if we think about the image we just saw, the first pixel, let's say the top left, they are almost all of them are black, which means none of them, which is the number of the number of the first pixel is white. None of them. So which means the probability of my first pixel being 1 on the condition that the image is actually 5 is equal to 0. All right. Let's jump back. So what is probability of the first pixel being 0, which is black, on the condition that this image is 5? Because there's only 2 things, like the pixel can only be 1 or 0, which means it will be 1 minus the previous one, which means if the probability of it being white is 0, then the probability of it being black is 100%. Then if the probability of it being white is, let's say, 20%, then the probability of it being black is 80%, 1 minus 20%. So let's see what we have. We have the probability. We have the, like, if we look at this complicated equation, we have all of them. We just need to go through the first pixel, go through the second pixel, go through the third pixel, calculating all of them. Then, yeah, I basically have the results. Then what it is like. So I'm giving out an image for each pixel. That's the calculated result. My pixel is white on the condition that this image is 5. For each pixel, I have probability. This I, xi, is each pixel. Like I is number, like the first pixel, the second pixel, till the dth pixel, like the number of features I have. And in this case, okay, if it's dark red, is it means it's 1. So the pixel being white is chance is 1. That's so sorry, it's opposite. I think so this is actually the pixel being 0, which is black. The chance of, let's say, the first pixel on the top left pixel, the chance of it being black is 1. But when it goes to the middle, where the dark blue shows, the chance of the pixel being black is about like 20%. So it's kind of reasonable that we have the probability for every pixel. So now what do? We're calculating it. I have a bunch of new images. Like in the first one, I keep calculating, okay, let's say the chance, let's say, so my probability of the first pixel being 0 is 1, and my pixel, the first pixel in my new image, is actually 1. So that is multiplied. So let's see, how do we explain it in a better way? Make it bigger, I think. So what is happening is I have a image, and it can be divided by pixels. And in my case, it's going to be 0. Let's change the color. So it's going to be okay. 0, 1, 0. Let's say 1, 1, 1, 1. All the others are 0. And I'm going to say the first, this is my first one, this is my second one, third one, fourth one, fifth one, sixth one, 7. Okay. The possibility of my first pixel is actually 0 in my case. Of the label, let's say it's 5. Or to make it more complicated, let's say it's 6. And in the based from our training data set, we know that do you remember that colored image showing that the first pixel of the pixel, so being 0, y equals to 6 was like, let's not make it 100% to make it, let's say it's a 0.99% of chance, which makes the x1 being 1, which is white, is 0.01. So that is what we get from the training data set. And in our case, our new data, this is a fresh new data. This is a fresh new data. And the first pixel is actually 1. The first pixel is actually 0. So the probability is 0.99. So let's say if they are all the same value to make our calculation much easier. The second one, the chance of being 1 is 0.01. And then the third one is 0, it's 0.99. Again, that forms our equation, which this is a multiply sign. I'm multiplying everything together. Is what the data set is like, is a data set pixel. And on the condition that this image is 6. So we calculate for all that. Then what do we have? Then what we have is the probability of this image on the left side. Probability of this image being 5 is actually 1. In the second one, or the probability of this image being 6 is about 99%. And the third image, which is so much complicated, but the probability of it being 5 is about 86%. Great. So that's based rule-based theorem or Bayesian theorem, whatever you like to call it. Of course, there are more. This is just the basic foundation of this Bayes theorem and Naïve Bayes. Feel free to ask me any questions. If you want, there is a little exercise for you to calculate, okay, what is a posterior, which is what is the chance of these people buys computer? Yes, it's 1, no, it's 0. And based on all these features, we have age, we have income, we have whether it's a student or not, whether it's a credit, or whether the credit rating is good or not. You can practice at home. I think I want to make it much shorter, the session much shorter, and so you don't get too bored from my questions. And next time, I want to ask for your ideas, whether you want to know more Bayes theorems, such as Monte Carlo method, Markov-Chain Monte Carlo, Gibbs sampling, Gaussian mixture. They get quite technical. I understand that when the topic goes too technical, it might not be very welcomed among the public. Another thing which I can think of is which might be fun because it's the reinforcement. The algorithm, the theorem is not very the theory is not very fun if you want to know the theory, but there is some company called OpenAI. They have this really interesting exercise, little task for you to do something which actually you have immediate feedback, immediate result, and that was pretty cool. So basically, what you can do is that based on it's kind of a little game. So you can train a model to predict how this rocket would tilt itself to land, like in a right way, something like that. There's a lot of little games like that, which we can use reinforcement learning to do that. I want to ask for your advice. Feel free to ask me any questions. And if you want to decide what the next topic is, please leave me a message either in my email account or leave it in the machine learning channel. It's machine_learning, machine learning channel in the Woman Who Codes Slack. So I'm going to, sorry.
Thank you so much.
Thank you. So I'm going to hand this